Good afternoon, ladies and gentlemen. This afternoon, I will be presenting to you rapid seismic screening tool that structural engineering community is using in the country, and also another risk assessment tool that we have been developing within the scope of the Seismic Research Network as it applies to the city of Ottawa. This seismic screening tool was initially developed by NRC in 1992, but subsequently had to be revised because in 2005, as you have heard this morning, National Building Code of Canada was revised, and we now have new hazard values, and the older seismic screening manual was not compatible with that. And Department of Public Works wanted to upgrade this because they have a stake in this, and as custodian of all the government buildings in the country, they wanted to be able to assess their buildings for seismic vulnerability. So I'd like to go through some of the background information that led to the updating of this screening manual, and then I will demonstrate how to use it. It's a fairly simple process which will give you some sense of what are the major issues. If one were to conduct a very rapid screening, what are the major parameters that structural engineers are interested in? As I have indicated, the earlier edition in 1992 was based on the US practice. It was Canadianized such that it would conform to the National Building Code of Canada. And then there were some other improvements introduced as well. And this included not only so-called walk-down survey, looking at the building from outside, but perhaps going inside and gathering more information, and if at all possible, looking at structural drawings and do a little bit more accurate assessment than our American colleagues would do at the time. The method is essentially based on picking up a number of empirical factors reflecting some of the primary vulnerability and risk parameters, and then multiplying them to get the first cut at this risk assessment process. If seismic screening shows high risk, then this does not mean the building has high risk. This simply means that it deserves further investigation, further analysis, and potentially retrofitting of the building. These indices are shown on this slide. Index A reflects seismicity. For example, if a building is designed today based on 2010 National Building Code of Canada, A would be 1 because we are using state-of-the-art knowledge that we have acquired over the years, and hence there's no reason to think that from seismicity perspective it is under-designed. But if a building was designed in 1960, that coefficient would be higher than 1. As the numbers increase, then vulnerability and risk would increase. Coefficient B would reflect soil conditions, and you've heard so much about it today. Obviously, for soft soils, risk would be higher, vulnerability of the building would be higher, and B would go up. And C would reflect toughness of the building, ductility of the building. This is something I will elaborate a little bit more in detail later on, but essentially not all buildings behave the same. Some buildings have inelastic capacity, ability to absorb seismic induced energy without causing failure, and these buildings would certainly be looked upon as favorable buildings, and this is the coefficient that reflects the differences between a well-designed reinforced concrete structure and a poorly, not even designed, non-engineered, unreinforced masonry construction. So this is where factor C comes into picture. Factor D, again, I will expand on this a little more, reflects irregularities in buildings. The simplest building that you can design, sort of a matchbox type of a building, would behave the best during an earthquake. The more irregularity you introduce, the higher vulnerability you have. and E would be the importance of building. This brings the exposure factor, whether you have a post-disaster hospital or you have an ordinary single-family home would make a difference, and this is where the difference would be introduced. And then there are non-structural indices, falling hazards, even though the structure may be standing up, but there may be other hazard associated with non-structural aspects, and this is reflected through F. And the combination of the two would give seismic priority index, and there are certain values assigned to that, and this would lead structural engineers to a decision as to whether further analysis is warranted and or retrofitting is warranted. I will not take too much of your time on seismic hazard. A lot has been said this morning, but the old practice was based on seismic zones, and the new practice, as reflected in 2005 and 10 National Building Codes, have uniform hazard spectral values for every municipality. In fact, in larger cities, a number of places in a given municipality, to do a more refined assessment of hazard. And this is an example of a table that would relate seismicity coefficient as it changes based on years. And these years not only reflect refinements in structural design processes, but it also reflects the level of knowledge in seismicity and the way seismic hazard is introduced in building codes. Soil conditions, again, we have newer classification in recent codes as opposed to the older codes. Here I've compared 1990 versus 2005. Dashed line is 1990. Dashed green line and the solid green line would give you the reference soil condition for 2005. And there's a bit of a difference in this case for Vancouver in the lower period range. But more importantly, as classes go up to B, C, D, E, and then seismic motion is amplified. And once again, this is reflected through factor B. And this table shows you the difference between what we have been using over the years and what we started using since 2005. And that had to be introduced into the seismic screening manual, which is what has been done. And this is a table that shows the effects of different soil conditions, but to further complicate the matter, in our recent 2 editions of the code, we have recognized the fact that amplification is period dependent. So if you have a 1-story building versus 10-story building versus 20-story building, the amplification would be different, and that is incorporated now, and hence you see period values on the left-hand side. Now, factor C, I said, introduces design and detailing practices employed by various building codes. And if you have sufficient strength and ductility, then the buildings would attract a certain amount of seismic force, and then they would yield, and they would become softer, their period will elongate, they will no longer attract as much forces, and they will dissipate energy, bounce back, and survive the earthquake. But if they don't have that, then obviously they will fail. Now, the older building codes did not have some of these bells and whistles that we've introduced over the years, recognizing that earthquake engineering is a fairly recent science prior to 1970s. We do not expect all our buildings having all these design and detailing provisions of recent building codes implemented. Here is an example. This is a building that completely collapsed in 2010 Chile earthquake, and it simply did not have strength, and it did not have proper detailing provisions of what we know, what should it be now. For example, the shear walls did not have sufficient boundary elements, sufficient reinforcement detailing. Here you see not enough splice length, bars pulling out, and there's another example where detailing is not done properly. So these types of buildings would have a higher D factor in this, C factor in the screening manual. And the differences in the way we introduce C factor in older codes and newer code has now been recognized, and we have, for different types of framing systems having different ductility and detailing requirements implemented over the years are introduced in this table in a very simple manner for rapid screening through factor C. I mentioned earlier that irregularities probably form the most significant aspect of seismic vulnerability of buildings. If you do have an irregular building, you're essentially looking for trouble. And here is another example in the same earthquake, in the same vicinity as the other building in Concepcion, Chile. We've seen this building and we said, wow, look at the irregularities, look at the offsets, look at the vertical strength and stiffness tapers, and yet nothing happened to the building. And then we started walking on the other side. Sure enough, wherever there was irregularity, there was a loss of a floor. So these irregularities we've seen over the years, over and over and over again, cause hazard, and they cause deficiencies in strength and ductility, and hence they have to be addressed in seismic screening manual. And this is done through factor D. Factor D introduces effect of vertical irregularities like the one you've seen, horizontal irregularities. Typically, when you have your elevator shaft near the end of a floor plan where it provides rigidity, doesn't allow the building oscillate, whereas at the far end, it starts oscillating, causing torsional effects, and then it increases demand on these far end columns. And hence, horizontal irregularities, vertical irregularities, and some of the other well-known irregularities like having short columns, soft stories are all addressed in this table through irregularity factor D. And this table also introduces pounding effect. If you have approximately more than 3-4 inches, less than 3-4 inches space between buildings, they're likely to hit each other, especially if the floors don't line up, then they cause a threat and high vulnerability in that building. And in our climate, deterioration comes into picture. Corrosion of reinforcement certainly does reduce strength and even ductility of that element. Exposure is introduced through building importance factor E. Here we can select post-disaster buildings, hospitals, police stations, even schools, even though they're regarded as of lesser importance than hospitals. We've now recognized schools being post-disaster shelters, and the importance factor has been upgraded a bit. And then special operational requirement facilities have a different category, and then all others. All others are essentially based on use and occupancy, number of and intensity of occupants, and there's a little bit of a simple equation that you have to go through to assess this is a densely populated building and hence it's important. And once again, these are the elements of that parameter N that one can quickly calculate, and then these are the importance factor introduced again pre-70 and post-70, 70 being the benchmark year for the introduction of recent modern building codes. In terms of non-structural hazard, we have falling debris, falling hazard. You may have a fairly well-designed frame, skeleton of the building standing up, but if you have unreinforced masonry infill walls or walls that are used as partitions or exterior cladding, facade, glass, if they start falling down on people, they're certainly causing threat to life safety, and hence this is also introduced. And at the end, we have a table that you're not expected to read. I will go through this again, that has all these factors A through F. And when you multiply that, you can see at the lower end, you get structural, seismic risk index based on which then one will have to make a decision. Now this is done now in the recent edition through software. It's a simple software. You can do a specific building analysis. Because it's a function of period, we did not expect the technical people who are going through the screening process to calculate building period, and hence there's this little tool that is provided in the form of Excel program that calculates building period and associated vulnerability factors. Once you calculate seismic priority index, if it is around 1 or 2, then you can say, well, this building is pretty much designed based on our current knowledge of earthquake-resistant design practices. So the building conforms to the recent NBCC, and hence we need not be worried. If it is approaching 10, but up to 10, then we may say, well, if we have lots of money, maybe we can look at this building again. And if it is between 10 and 20, once again, you have to weigh expenses versus, as bad as it sounds, how much safety you want to buy. Then you may or may not want to pursue. But if it is greater than 20, then you should definitely conduct more detailed analysis and potentially retrofit the building. If it's more than 30, just close the doors, definitely make a decision, don't let anybody know. And so this is kind of the screening process you go through. Now, very quickly, I'd like to show you this software and see if we could at least give you a feel for it. This is a, let me see if I could bring it to full screen. This is a Windows-based software, and you first have to open a new file, select the province. Let's look at, we're in Ontario, and perhaps select Ottawa. And once again, all these municipalities are listed here for which NBCC provides hazard values in the form of uniform hazard spectral acceleration. So if I go down to Ottawa, and select that, and if I say OK, then it would give you this table. And if you are working only in the city of Ottawa, you may not wish to carry your laptop. You can just print this, go around, and pick up your coefficients and calculate your seismic risk index. But if you want the computer to do it, then you say continue, and then select structural properties. It says province, Ontario, City, Ottawa. Then let's give it a title, otherwise it wouldn't like it. So I said test. Design MBCC, let's say it's an old building pre-1965. Frame category, moment resisting frame. Soil category, if we want to dramatize it, we can make it class E. And then we say calculate the period, and the period changes with structural framing system. And if you have a frame flexible, you have longer period. If you have shear wall structure, you have shorter period. So you have to identify that. In this case, we're dealing with reinforced concrete frame. We say OK, and then it also varies with building height. If it's a 2-story building, then let's say 4 meters per story height, 8 meters as an example. And then I say calculate, period is 0.36. And then do I want to use this value? Yes. Then it brings it here. Type of structure, this is where it calculates coefficient C, reflecting ductility built into this structural system. So I have to define concrete moment frame. And then we decided to dramatize, so I'm assuming we have vertical irregularity, horizontal, short column, soft story, and then let's make it a post-disaster building. And then we have falling hazards, maybe not this one. And then we say calculate risk. It says it is in the cutoff region of MBCC, because in MBCC, If we are in the short period range, we're allowed to use 2/3 of the values, provided that there is some ductility. Reinforced concrete inherently has a little bit of ductility, so I will say yes to use the cutoff value. And then it calculated seismic priority index is 70. Anything more than 30, 40 would raise flags. Here's an extreme example. This is on a soft soil, very short period structure, which means it would attract very high accelerations, all kinds of irregularities, hospital, and everything falling apart, falling hazards. So this is not unusual. Anyhow, this is an example that I wanted to show you quickly. We will now minimize the screen and then go back to our second tool. Second tool is a seismic risk assessment tool that has a general scope, but currently it uses hazard values derived for Ottawa, so I'm going to address Ottawa only. We have a rather interdisciplinary team at University of Ottawa. One of team members is at UBC. And then we have civil engineers. We have Professor Sawada from geography, bringing his GIS, GPS expertise. Kate Plodger is also, she is looking at social implications in terms of number of lives lost and dollar values lost, economic impact. So we are developing that module in addition to the engineering module. Dr. Tasfamarian has developed reinforced concrete module, and Amit is currently developing masonry structures model, and Eric is an undergraduate student who is integrating this tool with Google and Google Earth. So there is a rather comprehensive group of people working to come up with a tool which will give you, in a very quick but approximate way, seismic risk, so that you can then decide as to whether you should do further analysis. Now, risk can be defined, as was mentioned earlier, in a number of different ways, but it's literally, in this sense, building damageability and consequence of a failure. Now, why would building be damaged? If it's subjected to higher hazard, or if it's not well designed. So hazard and vulnerability would lead to building damageability. And then you have to look at consequence of failure, which is really the exposure factor. All of this would lead to risk. So if you have high hazard, very good designed building, your damageability may not be high. If you have the same high hazard, but poorly designed building, obviously its damageability will be high. Same damageability downtown Toronto versus in the middle of nowhere would have different risks. So this is where the exposure comes. So the idea is to capture all of these points. Again, you've been lectured all morning on seismic hazard, so I will pass through this quickly. But essentially, the tool uses whatever is provided by Geological Survey of Canada as the state-of-the-art understanding of Canadian seismicity. One can, depending on what level of analysis we will do, one can use either spectral accelerations or acceleration-compatible ground motions. And this is the microzonation map of City of Ottawa, developed at Carleton University in collaboration with Geological Survey of Canada. You've seen this, and the red region shows soft Leda clay of Ottawa, and then orange is slightly better, and then blue is better, and green is solid rock. So this map reflects hazard values as well as soil conditions. Now, our job is to put buildings on these and then try to assess how good the buildings are and how well they will perform in these regions. The work involves 3 stages. Tier 1, screening based on walk-down survey, which is comparable to the seismic screening manual that I just mentioned. Tier 2 would have more parameters, more detailed, and yet you still don't need computer program. Tier 3 would require full-fledged dynamic and elastic response history analysis, which is very rarely done, only done for important buildings. And Tier 1, building vulnerability, here what is important is how we approach deficiency in a structure. We look at increase in demand and decrease in resistance. It's very important to select the correct structural layout right at the onset. That would eliminate most of the problems. But if you choose an exotic building with all kinds of irregularities, same earthquake would increase seismic force and deformation demands in critical elements. So hazard can be same, but your selection of structural layout would have implications on demand. And decrease in resistance is how well you design it. That's the other parameter, both of which will lead to structural deficiency. And structural system also has contribution because everything else being same, shear wall buildings would perform better than frame buildings, for example. So all these factors considered, we can quantify building damageability in this scale, and then we can introduce consequence of failure, again, as I said, exposure, and here functional use, as in the case of post-disaster buildings, or occupancy, whether it's an office building or a farm building, or economic impact. All of these factors are considered. And then the software CAN-RISK was developed based on fuzzy logic because the whole concept is fuzzy. It's supposed to reflect lessons learned during previous earthquakes, and it reflects expert opinion. And now we're trying to make this a bit of a smart decision-making tool. The more you use it, the more it will improve and build up its own database. But as it stands now, it reflects weighted contributions of the parameters that I mentioned, and it eventually tells you this specific building in Ottawa, located on this soil, subjected to the seismicity defined in MBCC, would have marginal or critical or catastrophic risk. Now, Tier 2 evaluation brings in other parameters. Obviously, life is not that simple. We can't just say you have vertical irregularity. There are different types of vertical irregularities. Here you see on the top left corner a short column. Structural engineers would design these columns considering the entire height of the floor, but then you put a masonry wall as exterior enclosure or partition wall, then it provides unintended support. All of a sudden, shear stress is increased. This is unintended. This is called short column effect. And the Tier 2 assessment would differentiate that. And lower left is a building where you have strong beams, weak columns. Columns are responsible for overall strength and stability of the building. And in our current design practice, we have strong columns, weak beams. You look at a building, very deep, very strong beams, flimsy columns, then it should trigger a flag. And also you see in the middle a building that is suffering from pounding. Upper right corner, you see soft stories, and the lower right is a picture that I took in China that also has a soft story. And as you can see, little boxes increased. I'm not going to go through this. It just means to say that in Tier 2 evaluation, you do a finer assessment, finer details. Now, all of this has been incorporated into GIS. And this is what we call ArcCAN-RISK. And all one has to do is look at the microzonation, and the lines that you see and the numbers that you see reflect seismicity. So 0.33 G, for example, and then you would, and color coding reflects soil types. You would zoom in City of Ottawa. Here we're looking at University of Ottawa Engineering Building. And then when you zoom in, you see the building. And this is version 9 and version 10 of GIS, shows you three-dimensional beautiful pictures. But then here you're supposed to pick up visual details that you could see by doing a walk-down survey, enter that into CAN-RISC, and those are the building types, and then it would give you risk. Rather than taking your time, I'll continue and I'll show it to you on Google, the Google version. But let me tell you what is there to expect when this project is completed. Currently, we can do reinforced concrete buildings. There will be other structural types. We're almost finishing masonry buildings. There will be steel buildings completed as well. And then OFC hazard will be included. And Tier 3 analysis will be linked up through dynamic analysis program. Then another module, one PhD student is working on social implications and economic implications. So we will not only see building vulnerability, but we will see dollar values and estimated loss of lives. And there are plans to use it also, emergency response tool for first 72 hours. The same program has been introduced and used in Google environment. And at the risk of going to internet, maybe it does work, maybe I should first show you the slides that I have, and then we can look at internet, because this will give you an idea as to what to expect. We essentially go to Google, and this is Microzonation that was developed at Carleton University with showing soil types. And you zoom in further. You can even remove the soil color coding to improve visibility. And then here is a building that we've selected for investigation. And this is an apartment building at the intersection of Lees Avenue and Main Street in Ottawa. And then we see that it's a shear wall building, reinforced concrete, built in the 60s. And that information one has to acquire, of course. And then we fill in all the data at the top. And this is a 9-story building, apartment, occupancy 100 to 1,000 people range. And economic impact would be average. And then linguistically, it says negligible risk. And damage index is light. And numerically, it is 2 in a scale of 1 to 5. And risk in a scale of 0 to 1 is 0.13. Now, for argument's sake, of course, this is a 9-story building. It would attract less seismic forces. But if I reduce number of stories down to 1, let's say it's single story, then hazard will increase. Now we have moderate damage and critical risk. Now let me show you the actual Google map, and then we will zoom in somewhere in Ottawa, and maybe we can look at this red zone, which is Lida clay, worst type of soil in Ottawa. And I can maybe remove color coding to improve visibility. And then if I choose, here's a building. If I do a street view of the building, oops, I was expecting a building. I got lots of trees. Oh, here's a building. So the idea is to really zoom on this building and get whatever you could identify. For example, this building has 1, 2, 3, 4, 5, 9, 10 stories, and it has soft story, right? So you would go here and you would put 10 stories. Building type C1 is reinforced concrete frame. Vertical irregularity, yes, because it has soft story. Plan irregularity doesn't look like it, so I say no. Construction quality looks average. Year of construction will make up something. Let's say 75. And then building type is office. and occupancy would be over 100. Economic impact, let's say significant, let's say it has software companies. And then we say assess, evaluate, and I will get out of, by the way, it's soil class E, it picked it up itself. I will get out of here, and here it is. It's green, which means it's not too bad. So if I were to see risk and damageability, it says damage index light and negligible risk. Once again, even though this was on soft soil, it's reinforced concrete, built well, and 10-story building, low hazard, and it did not show high risk. But if I played with those parameters, the picture would certainly change. Going back to the presentation, I'd like to conclude my presentation by some idea on what we're doing in the city of Ottawa. We have started collecting building information, and this is done through students, either through walk-by survey or through Google, and we have developed handheld tools to be able to go around and record information while also taking pictures. And we looked at building footprints, and we gathered information from Statistics Canada and zoning data, and we have also color-coded year of construction. And to date, we've looked at over 6,000 buildings in downtown area. The shaded area is the area that we have covered, but we intend to cover the entire city. But outside of downtown core, it's mostly residential. Of this number, little over 5,000 are single-family, multifamily, duplex dwellings. And over 1,000 is multi-story buildings. And if you look at single-family homes or multifamily, essentially residential low-rise buildings, 93% are light wood frame construction. But this doesn't mean to say they do not have clay brick facade, but structural type, load resisting elements are wood, and 7% are masonry, unreinforced masonry. If you look at multi-story buildings, then concrete is 37%, 20%, and timber is 37%, and masonry is 33%, and steel is 10% of all the multi-story buildings. These multi-story buildings include apartments, condominiums, offices, hospitals, industrial buildings as well. If we look at only concrete construction, moment frames constitutes the majority, over 60%, and shear wall buildings 11%. Frame with unreinforced masonry infills. Infills are meant to be separated and not contribute to seismic resistance, but they almost always do. There's no guarantee that they're well isolated, and they do help until they disintegrate, so that they do form a different class of structures. Precast tilt-up is a very, very small percentage. And this does show distribution of building inventory in Ottawa. And judging by the parameters that I mentioned, looking at the different framing systems, different irregularities, and what we have in Ottawa, one can have a preliminary idea about seismic risk, and obviously one would have to look at these buildings one by one. One thing I did not mention is that in that seismic risk assessment tool, we don't only look at individual buildings. If a block is full of single-family homes, we could have an area that can be assessed. And so if you do block by block assessment, that's easier. Maybe choose a representative building. Or if you're interested on a specific building, you can zoom on and gather some information, keeping in mind that this is an approximate Tier 1 evaluation, and Tier 2 would improve results, but unless you do Tier 3, you would not be 100% sure. But if you're in a position to make a decision on a general area, obviously Tier 1 is the way to go to start. Thank you for your attention, and I'd be happy to answer any question that you may have.
Any questions? Please, Mark. At the back.
Yes, I was wondering if you presented this information to the Building Owners and Managers Association or the Risk and Insurance Managers Group, because this sounds like something they'd be very interested in.
No, we have not, and we have not decided as to how to make this tool available. We will make it available, but we will, in all likelihood, we will let them use it, because we're not in a position to assess somebody else's building and show that it's seismically deficient. But that's a very good question. I can give you an anecdote that will probably answer your question better. I was interviewed by Ottawa Citizen, and I mentioned that we're working on this tool. The next day I received a call from Deputy Minister of Public Works saying, "You mean to say you're going to tell us how bad our buildings are?" I said, "No, that's not the intent." So this tool is being developed. I will borrow Professor Ventura's disclaimer slide and insert it in, and then make it available somehow. But that decision has not been made yet. But it will be made available through web with a password so that it is not misused. I don't know if this answers your question, but it has not been fully developed, and hence it has not been fully presented anywhere yet. But we're just presenting it as a tool that's coming up.
Other questions? Terrific. Thank you.
Thank you.